Operations Management Applications. LP, or the Linear Programming Application, can be used in operations management to aid in decision-making about product mix, or also known as the product assortment or product portfolio, that refers to the complete set of products and/or services offered by a firm. Product scheduling, or the process of arranging, controlling, and optimizing work and workloads in a production process or manufacturing process. Staffing, or the process of hiring eligible candidates in the organization or company for a specific positions. Inventory control, or the stock control, is the process of ensuring that the right amount of supply is available within a business. Capacity planning, or the process of determining the production capacity needed by an organization to meet changing demands for its products, and other issues. An important application of LP is multi-period planning, such as production scheduling. The solution to production scheduling enables the manager to establish an efficient, low-cost production schedule for one or more products over several time periods, or weeks, or even months. The manager must determine the production levels that will allow the company to meet product demand requirements. Typical constraints include limitations on production capacity, labor capacity, storage space, and more, while minimizing total production costs. One advantage of using linear programming for production scheduling problems is that they recur. Example problem for production scheduling. Chip Who's is the owner of Who's Custom Wheels. Chip has just received orders for 1,000 standard wheels and 1,250 deluxe wheels next month, and for 800 standard and 1,500 deluxe the following month. All orders must be filled. The cost of making standard wheels is $10 and deluxe wheels is $16. Overtime rates are 50% higher. There are 1,000 hours of regular time and 500 hours of overtime available each month. It takes 0.5 hour to make a standard wheel and 0.6 hour to make a deluxe wheel. The cost of storing a wheel from 1 month to the next is $2. So the company wants to determine the regular time and overtime production quantities in each month for standard and deluxe wheels. So we need to set up a linear programming model for this problem. The objective function of a linear programming problem can be either of maximization or of minimization, depending on whether we want to maximize the profit or minimize the cost. The non-negativity constraint must always be included in LPP. So let the regular time and overtime production quantities in each month for standard and deluxe wheels the company wants to determine be denoted in the following table. We also want to determine the inventory quantities for standard and deluxe wheels. So let SI denote the number of standard wheels held in inventory from month 1 to month 2, and DI denote the number of deluxe wheels held in inventory from month 1 to month 2. Our aim is to minimize the total production and inventory cost for the two wheels, the standard and deluxe wheels. So the objective function is given as minimization, or production cost per wheel times number of wheels produced plus inventory cost per wheel times number of wheels in inventory. The constraint for production of standard and deluxe wheels in month 1 is production month 1 is equals to units required plus units stored. So for standard is 1,000 and deluxe is 1,250. So the constraint for production of standard and deluxe wheels in month 2 is units required minus units stored. So for standard is 800 and deluxe is 1,500. The time constraints are Regular hours used month 1 is less than or equal to regular hours available month 1. So, 0.5 times standard regular sub 1 plus 0.6 deluxe regular sub 1 is less than or equal to 1,000. And overtime hours used for month 1 is less than or equal to overtime hours available for month 1 is zero point 0.5 standard overtime plus zero point 0.6 deluxe overtime is less than or equal to 500. And for regular hours used for month 2 is less than or equal to regular hours available for month 2 is zero point 0.5 standard regular sub 2 plus zero point 0.6 deluxe regular sub 2 is less than or equal to 1,000. And for overtime hours used for month 2, less than or equal to overtime hours available for month 2 is zero point 0.5 standard overtime plus zero point 0.6 deluxe overtime is less than or equal to 500. So here is the computer solution. So the objective function value is 67,500. And for the solution summary, so thus recommended production schedule is for standard we have the regular time of 500 and for deluxe is 1,250 for month 1 and for overtime is standard is 500 and deluxe is 0. And for month 2 is regular time for standard is 200 and regular time for deluxe is 1,500 and for the overtime is 600 for deluxe and 600 rather for standard and 0 for deluxe. So no wheels are stored and the minimum total cost is $67,500. Workforce assignment. So workforce assignment or problems frequently occur when production managers must make decisions involving staffing requirements for a given planning period. So workforce assignments often have some flexibility and at least some personnel can be assigned to more than one department or work center. National Wing Company or NWC is gearing up for the new B-48 contract. NWC has agreed to produce 20 wings in April, 24 in May, and 30 in June. Currently, NWC has 100 fully qualified workers. A fully qualified worker can either be placed in production or can train new recruits. A new recruit can be trained to be an apprentice in 1 month. After another month, the apprentice becomes a qualified worker. Each trainer can train 2 recruits. The production rate and salary per employee type is listed below. So the type of employees are production, trainer, apprentice, and recruit. The production rate or the wings per month is production is 0.6, for trainer is 0.3, apprentice is 0.4, and recruit is 0.05. The wage per month for production is $3,000, for trainer is $3,300, for apprentice is $2,600, and for recruit is $2,200. At the end of June, NWC wishes to have no recruits or apprentices but have at least 140 full-time workers. Define the decision variables. So Pi equals to number of producers in I, or where I is 1, 2, 3 for April, May, and June. And T sub I equals to number of trainers in I, where I is 1 and 2 for April and May. And A sub I equals to number of apprentices in month I, where I is 2, 3 for May and June. And Ri is number of recruits in month I, where I is 1 and 2 for April and May. Define the objective function. So minimize total wage cost for producers, trainers, apprentices, and recruits for April, May, and June. So minimization is 3,000 P sub 1 plus 3,300 T sub 1 plus 2,200 R sub 1 plus 3,000 P sub 2 plus 3,300 T sub 2 plus 2,600 A sub 2 plus 2,200 R sub 2 plus 3,000 P sub 3 plus 2,600 A sub 3. Define the constraints. So the total production in month 1 or April must equal or exceed contract for month 1. So 0.6 P sub 1 plus 0.3 T sub 1 plus 0.05 R sub 1 is greater than or equal to 20. So the total production in months 1 to 2 or April and May must equal or exceed total contracts for months 1 to 2. So 0.6 P sub 1 plus 0.3 T sub 1 plus 0.05 R sub 1 plus 0.6 P sub 2 plus 0.3 T sub 2 plus 0.4 A sub 2 plus 0.05 R sub 2 is greater than or equal to 44. So the total production in months 1 to 3 is April, May, and June must equal or exceed total contracts for months 1 to 3. So 0.6 P sub 1 plus 0.3 T sub 1 plus 0.05 R sub 1 plus 0.6 P sub 2 plus 0.3 T sub 2 plus 0.4 A sub 2 plus 0.05 R sub 2 plus 0.6 P sub 3 plus 0.4 A sub 3 is greater than or equal to 74. Define the constraints. So the number of producers and trainers in a month must equal the number of producers or trainers and apprentices in the previous month. So P sub 1 minus P sub 2 plus T sub 1 minus T sub 2 equals 0. And P sub 2 minus P sub 3 plus T sub 2 plus A sub 2 equals 0. So the number of apprentices in a month must equal the number of recruits in the previous month. So A sub 2 minus R sub 1 equals 0 and A sub 3 minus R sub 2 equals 0. Each trainer can train 2 recruits. So 2 T sub 1 minus R sub 1 is greater than or equal to 0. And 2 T sub 2 minus R sub 2 equals greater than or equal to 0. In April, there are 100 employees that can be producers or trainers. P sub 1 plus T sub 1 equals 100. At the end of June, there are to be at least 140 employees. So P sub 3 plus A sub 3 is greater than or equal to 140. So non-negativity is P sub 1, T sub 1, R sub 1, P sub 2, T sub 2, A sub 2, R sub 2, P sub 3, A sub 3 is greater than or equal to 0. So the solution summary. So P sub 1 equals to 100 and T sub 1 is 0 and R sub 1 is 0. P sub 2 is 80 and T sub 2 is 20. A sub 2 is 0 and R sub 2 is 40. P sub 3 is 100 and A sub 3 is 40. So the total wage cost is $1,098,000. And producers for April is 100 and trainers is 0, apprentices is 0 and recruits is 0. And for the month of May, the producers are 80, trainers 20, apprentices 0 and recruits 40. And for the month of June, producers 100, trainers 0, apprentices 40 and recruits 0. And in July, producers is 140 and trainers, apprentices and recruits are all 0. Product mix. Product mix, also known as a product assortment, refers to the total number of product lines a company offers to its customers. For example, your company may sell multiple lines of products. Your product lines may be fairly similar, such as dishwashing liquid and bar soap, which are both used for cleaning and use similar technologies. Or your product lines may be vastly different, such as diapers and razors. Floataway Tours has $420,000 that can be used to purchase new rental boats for hire during the summer. The boats can be purchased from 2 different manufacturers. Floataway Tours would like to purchase at least 50 boats and would like to purchase the same number from Sleek Boat as from Racer to maintain goodwill. At the same time, floatway tours wishes to have total seating capacity of at least 200. Formulate this problem as a linear program. So boat, Speedhawk, Silverbird, Catman, and Classy. So builder, Slick Boat, Racer, and Racer. So the cost for Speedhawk is $6,000 and Silverbird is $7,000. For Catman is $5,000 and for Classy is $9,000. So maximum seating capacity for Speedhawk is 3 and for Silverbird is 5, for Catman is 2 and for Classy is 6. So expected daily profit for Speedhawk is $70 and for Silverbird is $80. For Catman is $50 and for Classy is $110. Define the decision variables. So x sub 1 equals number of Speedhawks ordered. X sub 2 is number of Silverbirds ordered. And for x sub 3 is number of Catmans ordered, and x sub 4 is number of Classys ordered. Define the objective function. So maximize total expected daily profit. So maximization expected daily profit per unit. So x is number of units. So 7x sub 1 plus 80x sub 2 plus 50x sub 3 plus 110x sub 4. So define the constraints. So spend no more than $420,000. So 6,000x sub 1 plus 7,000x sub 2 plus 5,000x sub 3 plus 9,000x sub 4 is less than or equal to 420,000. And purchase at least 50 boats. So x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 is greater than or equal to 50. So number of boats from Slick Boat must equal number of boats from Racer. So x sub 1 plus x sub 2 equals x sub 3 plus x sub 4, or x sub 1 plus x sub 2 minus x sub 3 minus x sub 4 equals 0. Define the constraint. So capacity at least 200. So 3x sub 1 plus 5x sub 2 plus 2x sub 3 plus 6x sub 4 is greater than or equal to 200. So the non-negativity of variables is x sub 1 is greater than or equal to 0, for I is equals to 1, 2, 3, and 4. So here is the computer output. So solution summary. So purchase 28 Speedhawks from Slick Boat. Purchase 28 Classys from Racer. Total expected daily profit is $5,040. The minimum number of boats was exceeded by 6 surplus for constraint number 2, and the minimum seating capacity was exceeded by 52 surplus for constraint number 4. Blending problems. So blending problems arise whenever a manager must decide how to blend two or more resources to produce one or more products. In these situations, the resources contain one or more essential ingredients that must be blended into final products that will contain specific percentages of each. Blending problems occur frequently in the petroleum industry. For example, blending crude oil to produce different octane gasolines. And also in chemical industry, blending chemicals to produce fertilizers and weed killers. And also food industry, blending ingredients to produce soft drinks and soups. Ferdinand Feed Company receives 4 raw grains from which it dries pet food. The pet food advertises that each 8-ounce packet meets the minimum daily requirements for vitamin C, protein, and iron. The cost of each raw grain as well as the vitamin C, protein, and iron units per pound of each grain are summarized on the next slide. Ferdinand is interested in producing the 8-ounce mixture at minimum cost, while meeting the minimum daily requirements of 6 units of vitamin C, 5 units of protein, and 5 units of iron. Define the decision variable. So x sub j, or the pounds of grain j, is 1, 2, 3, and 4 used in the 8-ounce mixture. Define the objective function. So minimize the total cost for an 8-ounce mixture is 0.75 x sub 1 plus 0.90 x sub 2 plus 0.80 x sub 3 plus 0.70 x sub 4. Define the constraints. So total weight of the mix is 8 ounces or 0.5 pounds. So x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 equals to 0.5. So the total amount of vitamin C in the mix is at least 6 units. So 9x sub 1 plus 16x sub 2 plus 8x sub 3 plus 10x sub 4 is greater than 6. So the total amount of protein in the mix is at least 5 units. So 12x sub 1 plus 10x sub 2 plus 10x sub 3 plus 8x sub 4 is greater than 5. The total amount of iron in the mix is at least 5 units. 14x sub 2 plus 15x sub 3 plus 7x sub 4 is greater than 5. So the non-negativity of variables of x sub j is greater than or equal to 0 for all j. So here is the computer output. Thus, the total optimal blend is about 0.10 of grain plus 0.21 pounds of grain 2 and 0.09 pounds of grain 3 and 0.10 pounds of grain 4. The mixture costs Fredericks 40.6 cents. So that's all for our report. Thank you.